All right, apologies for the brief false start there. Had a bit of an issue with my screen capture. I think it's all set now. This is my first time checking out this game. I'm kind of excited for it. I always love a gnarly, way too detailed computer simulation game. So let's, sorry, moving some things around my workspace. Let's get to it, and let's get started. Congratulations, you have been abducted. We are testing you. The rules are simple. Build a functional computer or you will be eaten. Good luck. A signal flows from input to output. In the upper left corner under input, there is a green icon. Click on it to turn the input component off. Notice that the output component is turned off. This is because the signal stopped flowing from the input component. Click the gray buttons. Oop, there we go. We are very impressed with how well you completed the last test. We have decided you are probably not a plant. In this level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level, or you will get stuck next level. Alright, what does the NAND gate do? Check. Correct. With this component, you can build everything else in your computer. Yes, I already know how a NAND gate works. These early ones I expect to blow through pretty quickly before I have to start using my brain. Now that you have unlocked the NAND gate, it is time for you to build a circuit. Last level, you made the table that described the circuit. In this level, you build the circuit that matches the table. Using NAND gates, build the NOT gate. Yeah. How do I... Okay. Maybe I do not want that option set. Clicked something, and maybe it's not what I want. I don't actually know how the controls in this work, so... Okay, can I click and drag now? I can. Alright, there we go. This unlocks a NOT gate and level map mode. Click onwards and you will see. Alright, here's our level map. There's WAS to Japan, arithmetic, memory, CPU architecture. We get into programming, CPU architecture 2, functions, and assembly challenges. Alright. But for now, we sit at an AND gate. Adjusting for brain size, I'm doing well, huh? Create the circuit that matches the table. Okay, yeah, this is just, doing an AND gate. Run. And we have an AND gate. This is a NOR gate, which is... let's see. Onwards, and our last one is going to be an OR gate, which is just these pieces. Onwards. Okay. Next. Create a circuit that is always green. All right. That's input or not input. Do this way. Yeah, that looks cleaner. This level unlocks your first manual page. This one is important. Make sure you understand it. De Morgan's laws. Yep. That's why I was able to build all of those so quickly. We have an always on, we have an always off, and we have De Morgan's laws. All right. As you know, these tests culminate in building a functional computer. Species that are capable of finishing are considered sentient by law. This is the main reason we don't eat you afterwards. Output green on the second tick only. Okay. So that's 1 and not 2. There's probably another pattern that also would have worked for that, but that was the easiest one for me. Last level, you built a circuit that was green when we were at the second tick. Okay, so this is an XOR. This level is difficult. Let's see. There's 2 ways to do this. But I think I'm going to do it this way. So it's A or B, and not... Oh, I have a NAND. Let's use a NAND. That's an AND. NAND. That should be what we want. Okay, got the XOR, got a manual entry on truth tables and universal gates, and I have an online profile. Can I read the manual from here? No, I have to be bigger or gate, bigger and gate. Okay. Manual, here we go. Universal gates. And truth tables, yeah, nothing special. Create an OR gate with 3 inputs. Okay. In real life, you wouldn't do this. You would actually build a multi-input OR gate directly from transistors. But we can forgive the game for trying to make it easy on me. And should go for that 3-input AND gate. Okay, this is going to be the same. Okay, there we go. That unlocks a 3-input AND gate. Now we have just one more in basic logic before we start getting up to our 2 halves, which are arithmetic and memory. All right. I will go ahead and get this one done. The inverse XOR gate, known as XNOR. Okay. And where's my knot? There's a knot. That was easy. Okay, so now I have arithmetic and memory, and they are kind of intertwined. I guess I'm just going to kind of keep going by tier and not... Oh, what is this? Converting decimal into binary under time pressure. Toggle the bits in the level panel. You must beat level 3 to pass. 6, 11, 12, 14, 22, 21, 2, 4, 19, 31, 3, 2, 37, 62 is gonna be that. 32. Ah, whoops. Misclicked. But I reached level 4, and that's all that matters. Hopefully you notice there's exactly one way to write each number in binary. The value of each digit is always double the previous digit. Onwards. Okay, what do we have here? Because we are so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects sock pairs broke on the machine. This level has 4 inputs. Output green when 2 or more of them are green. Tip, don't overthink. Okay. So 2 or more of them. Alright, I'm gonna do what they say, and I'm not gonna overthink it. And what I'm gonna do is I'm gonna just pair up all the possible pairs with AND gates. I'm sure there's a nicer way to do this. But I'm gonna not overthink it, like they said. I'd already lost track of what I'm doing with my different gates. Okay. First one. Second one. Third one. Okay, so this is all the outputs from bit 1. Bit 3. Your bit 1. With bit 4. Alright. And then we have bit... Woohoo. Bit 2. Don't love the way that it's trying to do that. Bit 2 with bit bit 2 with bit 3, bit 2 with bit 4, and bit 3 with bit 4. Okay, I can make this cleaner. I'm gonna delete it all. Input, output. We have 3, 4, 5, 6. Each of those feeds into one of these 3 input ORs, which will feed into a 2 input OR, which will feed to the output. Okay. Perfect. Okay, now all I have to do is try to make the inputs look not truly awful. So this is bit 1 with bit with bit 2, bit 1 with bit 3, bit 1 with bit 4, bit 2 sure, with bit 3, bit 2, connect you somewhere there. I don't like that path. Bit 2, like there. That's fine. With bit 4. And lastly, bit 3 with bit 4. Alright, that's mostly clean. I'm sure there's a better way to do this, but a bunch of ands and ors is not the worst thing in the world. Using a maximum of 3 components, output green only when an odd number of inputs are green. Okay. So this is definitely a... I mean, I don't think this is going to do what I want, but I'm going to try it just so I can see where it goes wrong. I wish their drawing was a little bit more like KiCad's, because that's what my brain keeps trying to do. I keep trying to route things like up first or left first, and this game doesn't like that. Oh, that does do what I want it to do. Cool. And last one on this tier. In our education system, we traditionally teach by tricking students into doing the wrong thing and then teasing them. I'm not sure it benefits the students, but the teachers love it. Create a circular dependency. This is a circuit where the input of a component relies on its own output. In a circular dependency situation, it is not possible to determine the output of a component, because you would first need to determine its input, which relies on the output, blah 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 blah. The goal is to create it. Okay. Well, I'll just, dependency involving at least 2 components. Fine. Alright. We got a new book entry on circular dependencies, which I will probably never read. The output component of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. Okay. So this is ultimately a bunch of ands and ors, I think, or mostly ands and nots. So let's... Oh, but it's a binary counter. Okay. 1, 2, 3, and 4. So 1 is the odd circuit that we did before. That's an easy start. We know how to do this. Because whenever the number's odd, we'll have a 1 set. Okay, so that's the easy part. 2 needs to be set if there are 2 or 3 outputs, which means that any pair is set but not both. No. One, two, three, four, five. Yeah, there are 6 possible pairs, and I can definitely do this with a bunch of AND gates, but that doesn't make me happy. I really wish this was kind of better expanded to show... Okay, so if there's 2 set, those 2 set, and not those 2, that's a 2. Those 2 set and not those 2, those 2 and not those 2. Those 3, that's a 2 output. 2, 2. Alright, well, I'm going to start with my 4th bit output, because I know how to do that one, and then I'll figure out bit 2. 4th bit is just all of the previous okay, that's the 4's place. Everything is set. 4's place. That just leaves the 2's place, which needs to be set if at least 2 are set. And I can do this with 6 ANDs and a bunch of ORs, which just checks all the pairs. I don't love that. There's got to be a better way to do it than that. There is a hint. Is what you did in Double Trouble, except when all the 4s are on. Do I remember Double Trouble? Double Trouble. Okay, and this is what I did here. I did just do all the ANDs and ORs in this one. Alright. Fine. We'll do it. I don't love it, but... 1, 2, 3, 4, 5, 6. Then 2, 3 input OR gates. 1, 2 input OR gate. 2 input OR gate. Nope. 2 input OR gate. Okay, this is just going to be slightly tedious to wire up. Let's just get bit 1 to its 3 things. With bit 2, I'm just giving up and letting the spaghetti happen at that point. At this point, I just don't care anymore. This is bit 2 to 2 of them with bit 3 and bit 4. And then here we just have bit 3 and bit 4. Okay, this should be it. Did I mess up? 6? Oh, right. It needs to be not when there's... so that's and not a 4. Yep. Okay, that should be right now. Okay. Onwards. We measure the universe with numbers, so your machine must learn to count. Treat inputs as 0 or 1, depending on whether they are red or green. Add them together. Okay. So I know how a half adder works. There's my AND gate. There we go. And run it. Onwards. Okay. Delay lines. This level introduces the delay line component and takes its input and outputs it one tick later. Construct a circuit that outputs the same as the input, just delayed by 2 ticks. Alright, well, that's 2 delay lines. Run! Okay, back to arithmetic. Or do I just want to kind of finish this branch of the memory stuff and be done? Yeah, whatever. I'll just keep going across tier by tier. The input and output of this level are using bytes instead of bits. One of the 2 new components takes a byte and splits it. Figure out how to double the input number. Okay. So we have a, whoops, a byte splitter. We have a byte joiner. And if we're doubling, we're just shifting by 1. So that's gonna be this. And 7, shifted by 1. Run it. In the previous level, we added together 2 inputs. This time we add 3. Once again, add the inputs together in binary, such that the result is either 0 or 1. As with normal addition, if the result cannot be described with 1 digit, set the carry to 1. Alright, let's see if I can remember how to do a full adder off the top of my head. So we're going to start with A XOR B, XOR C, and that's our sum. And then carry is... Ooh, do I remember carry? So we have a carry if any 2 of them are set. So it's either that, and let's pull this off there, so that's a little cleaner. And then I can pull this one off of here. That and that. So if those 2 are both high, then we output a carry. Or these 2 are both high, we output a carry. And this one will never be high if both of these are high. I think this is it. Let's see, did I remember that? Yeah, that's a full adder. And I got an achievement for doing it in 5 components. Because I apparently remember how full adders work. Okay, onwards. In the previous level, you learned how we don't allow circular dependencies. Now you must learn the one exception. It's going to be delay lines, right? Yep. Input does not influence the rest of the circuit until the next tick. Square pins, never okay. Output red on the even ticks and green on the odd ticks. So this is... I mean, this is just a clock, right? Which is just a a delayed inverter. Yeah, okay. That was easy. Now we've got components output different values on the same wire, you get an error. However, some components have gray output pins. These are not outputting... Okay, so this is high Z or whatever you want to call it, depending on the datasheet you read. Free state. Use 2 NOT gates and 2 switches to build... Okay. So, since these are switches, this is going to be a wired OR of some sort, I'm assuming, to start with. And then an XOR with an OR as its last stage is A and not B, or B and not A, right? So this will be something like, I don't like that, let's do it this way. B and not A, or A and not B. Maybe trying to actually connect. There we go. And if I run that, yeah. So I got a switch and an 8-bit switch. Okay. We are experimenting with how backgrounds influence cognitive functioning in Earthlings. When invert is green, output the opposite of value, otherwise just output value. This is an XOR. Using an XOR as a controllable inverter is a very standard bit of electrical engineering work. Keep my connections connected, please. There we go. Despite the funny background, you figured out this was just the XOR gate in disguise. Well done. Onwards. Alright, looks like we've got some more arithmetic to go before we get to go further up the memory stuff. You may think it is unethical to eat all the Earthlings that don't win the competition, but actually it is okay because you lived good lives in the wild and we don't let the meat go to waste. Or each bit of the input bytes and output the result. Okay, this is going to be messy. So we've got 2 8-bit inputs. An 8-bit output. And bring these down here. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8 of these. Ooh, that panning is very sensitive. All right, let's get these wired in. This is definitely the most tedious part of this. Ooh, don't love that. Let's do it this way. Also don't love that, but... yeah, whatever, doesn't matter. It's gonna be a little bit of spaghetti. I'm trying to keep the spaghetti under control, but it is difficult with this interface. Okay, that should be what we want. What? Oh, helps to actually connect. Yep. Helps to connect the inputs too. Onwards. Our previous model of brain size being the main predictor of intelligence was naive. Tool making and usage is key in the early evolutionary stages of developing intelligence. Therefore, the number of arms on a creature is clearly the main predictor of intelligence. Did you know there are sea creatures from your planet with 4 times as many arms as you, and they're doing better in tests? Not each bit of the byte input. All right. So we're going to take an input and an output and a bunch of NOT gates. And then we're going to move everything much closer together so I don't have to draw long wires. Hey, copy and paste. All right, run it. And again, it helps if I actually connect things. Run it. Add the 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the inputs and potentially a carry. The result does not fit. Carry. Okay, you have a 1-bit adder, right? Yeah, it gave me that from a previous one. This is just going to be, again, very messy. All right. Should have done this before I copied and pasted everything. That's okay. Also, that's the output, not the carry, isn't it? Yep. Six, 7. Final carry output goes here. Recombine. 1, 2, 4. Oops. 8, 16, 32, 64, 128. We're going to redo carry this way so that it's a little better delineated. All right, and now we just get to try to add all of our bits, which is just, again, gonna be messy. Okay, that should be a byte adder. And that unlocks a byte adder. Okay. To know the difference between things, you need subtraction. To get subtraction, you need negative numbers. Level introduces 2's complement, the most common representation for negative numbers. Here the highest digit is negated, blah blah blah. Okay, ready to race, start. 1. 15. Negative 1. Negative 2. Negative 3. Negative 7. Negative 11. Whoop. Negative 7. Negative 15. Negative 3. Negative 16. -8. -26. -12. -1. -14. -6. -14. -25. -17. Oops. Alright. Timed out. Good job, we reached level 4. And yes, I know how to do these things. Negative numbers onwards. Even though he did not pass our tests, we decided to keep the dog. Unlike most Earthlings, he is fluffy and follows simple instructions well. We might want to team you two up, since you complement each other's shortcomings well. When the bit selector is red, output byte A. Otherwise, output byte B. Okay, so this is just switches, right? We have 2 switches. We have a not. Where's my not? On one of them. See if I get the not on the right one to begin with. I probably won't. That's okay. And then you go there, you go there, you go there, and you go there. Run. Okay, yep, that's what I thought. Got it backwards. Not a big deal. Where's my not? Let's do it here instead. Alright. Onwards. Taking the input as signed, make a component that takes a number and negates it. Alright, so that's just invert and add 1, right? So that's a not, an adder, and a constant. And since I know that this treats unused inputs like they have pull downs on them. Okay, done. This level has 2-byte inputs and 2-byte outputs. Copy from one of the inputs to one of the outputs. The first bit input determines which input you should copy from. The second determines which one you should copy to. Okay, so this is just a bunch of switches. Okay, so we're gonna have a crossbar like that. We're gonna have our inputs and outputs. And then we're gonna have, can I rotate these? Ooh, I can. Fancy. Okay. So when this is 0, that one's off. That one's on, and I assume it's going to be the same for this one. Oh no, that's fine. I'm gonna pull it in instead. Yeah. And then you go there, and these need to be connected. Look at that. Isn't that beautiful? I think this is the first one of these that I've managed to make look nice. Delay line only allows us to save a value for one tick. Sometimes a value that can save a value for a component that can save a value for longer periods of time is useful. We want to build such a component. We have two inputs. Okay, I'm making a latch. So a latch, when save enable is on, we want to store the new value. Store the new value, like so. And when save enable is off, we want to save the old value, which will be like this, and a not. What did I do? Oh, I didn't actually connect this signal. That's what I did. There we go. Unlocks 1-bit memory. Onwards. Create a circuit that can save or load a byte. When the first input bit is load, when the second input bit is on, save the input byte. Okay. Did I get an 8-bit memory? No, I didn't. Okay. So I'm gonna have to do this with a bunch of these. 3, 4, 5, 6, 7, 8. Excuse me. Those all come together on this side. This thing gets to connect to the load. Sure. We have input here. Input here, thank you. Ooh. 5, 6, 7. Ooh. 7. I'm actually going to move this back a little bit so that this will look decent. All right, and then these ones all need to go in. I should really think about coloring my wires on some of these, but so far I haven't really needed to debug things too badly, so it's been manageable. All right, I think that's it. All right, onwards. Can switch a signal between two pins. Is this not? Okay. Am I missing something? I'm not missing something. Okay. 3-bit decoder. Make a circuit that selects one output for each of the 8 combinations. No more or less than 1 bit should be green at a time. Okay. Oh, okay, I can middle click to pan. That's better. Okay. Well, this is what we're gonna do. We're gonna have 8 3 input and gates. Connected up to our outputs. Oops. 4, 5, 6, 7, 8. And then for each of these inputs, we're going to have the value and its inverse. So we're going to have 3 values. And their 3 inverses. And then for each of these, we just hook them up to the appropriate input. So, wait. So that's 0. Sorry. Already getting it wrong. 1, 2, yeah, okay. So there is nothing for 0. 1 is going to be 1, 0, 0. So that'll be 1, 0, 0. Then this is going to be 0, 1, 0, 1, 1, 0, 0, 0, 1. Oops. 1, 1, 0. One. I have definitely messed something up somewhere. All right, we're starting over. All right, so 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 101 111 101 110 111. Oh, because we are supposed to have a 000 in here. That's my problem. Okay. Now that I know what I'm doing wrong. Alright, starting with 000. Now this is going to make sense. Let's see here. 0, 1, 0, 1, 1, 0, 1, 0. Oops. 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. Assuming no mistakes. And of course, already a mistake. Okay. 0, 1, 2, you're 3. So you should be 1, 1, 1, 0. There we go. Only one mistake. That's not awful. We had our intern add a disable bit to this component. We were tired of looking at him running in circles, and we're looking for other pointless and tedious tasks to give him. So we have this 3-bit decoder. Okay. We're getting dangerously close to, like, real components here. I suspect these are going to start getting hard and not just tedious soon. Create a device that can OR, NAND, NOR, or AND 2 inputs. The third input will be the instruction. An instruction is just what we call the number that determines what to compute. Okay. Do I get... Really? I don't have 8-bit logic pieces? You're gonna make me build all 8 of these bits? What are the other ones? Can you fit 4 bytes of memory in this limited space? In this level, you have to build a circuit that can save or load from 4 different bytes of memory. You're given 1 bit determines if you are to load, and it determines if you are to save. You have 2 address bits. With 2 bits, there are 4 combinations, 1 for each byte of memory in this level. Alright, well, here's our output. I'll just put that up there for now. We have 8-bit registers. Do I get my decoder? I have a 1-bit decoder. Oh, okay. How do I want to do this? This is very little space is really the thing. I need a 2 to 4 decoder, which I don't have. I do have this, which is a 1-bit decoder. And then I have another 1-bit decoder. And then I guess I need 4. I don't love this. 4 1 AND gates. 4 8-bit registers. I guess I have the space. It's just not a ton of space. Okay. Oh, these need to be actually 3 input ANDs, and I need 2 banks of them. That sucks. 1, 2, 3, 4. Oops. Do I have redo? There we go. Move these over. Let's do that for our doodah. And actually load is the top one, so that works out really well. Perfect. Pull these all over one. Okay, there's all of our outputs. Now, loading happens for each of these when the load bit is set. Actually gonna get rid of this for a second. Down here. And their particular combination of input bits is set. So this one will be 1, 1. Doesn't actually matter which ones they're each on. 1, 0, 0, 1, 0, 0. Okay. Now I just need to do that again. Somewhere, some way. Yeah, let's just erase all of this. Can I? No, I can't. Okay, how do I want to do this? We have 3 input ANDs for 1, 2, 3, 4. Each of these will be on a decoder. Each of these is on load. And each of these is on two of these. What a mess. And then these go to the load outputs of each of these. Oh, and the value, of course, can just get routed straight in. And then I just need 4 more AND gates packed in here. It's not those ones, though. 1, 2, 3, 4. Oh my god, it's gonna work. Let's get a bus for the save bit up here. And then again, each of these gets routed. 1, 0, 0, 1, 0, 0. And then... Ooh, now here's the question. Did I put them at all in a sane order? Short circuit. Ooh. Okay. Oh, I did it. We have a 256 byte version. Unlocks 256 byte RAM. Heck yeah. Onwards. That counts increments once per tick. Additionally, there should be an option for overwriting the counter with a given value. Okay. So this is a register. Action is count. Okay. So we have a adder that's going to take in our output value and a single on bit. And it's going to output our value, which needs to be filtered, which is a switch, which needs to be on when this bit is 0, so we need to invert that. Oh, I don't want to register, do I? Okay. That's fine. We just always want save and load to be on. Right? Because, yeah, if save and load are both on, it should always be incrementing. And then the other option is we have another 8-bit switch, which will hook up here when this is low. There we go. 8-bit counter. Increments each tick unless overwritten. Onwards. Okay, well, now it really wants me to solve this ALU that I was trying not to do. What's this one? Registers. Oh, this looks like a puzzle. Time to create your master project, implementing the Overture computer architecture. This will be an actual Turing Complete machine, a true computer in every way. I have locked the red components of this level in place since you always make a mess and don't leave enough space. Hey! The mess you make from now on is saved between levels. You no longer get to start fresh each level. In this level, you need to create a circuit which can copy from a source to a destination. It can be one of 6 registers, reg 0 to reg 5. Okay. Now we're getting into actually interesting circuits. Input. Okay. Do I have a... a decoder yet? I don't, do I? I have a 3-bit decoder. Oh, but that's enough, isn't it? Because my inputs are... yeah, only 3 bits. Source and destination. Okay, yeah. So this is just a bunch of switches in a big old matrix is what it is. This feels like a maybe save for the morning project. It's already 10 p.m. here. Alright, what's this section? Create a device that can OR, NAND, NOR, or AND 2 inputs. The third input will be the instruction. An instruction... okay. I can do something with the way these instruction bits are coded so that we are inverting if bit 2 is set. And then we only have to switch between OR and NAND based on bit 1. That's a little bit nicer. And switching between OR and NAND is really choosing whether or not to invert the inputs. Yeah, I think I can do this all with a NAND array and inverters on the inputs and the outputs depending on the control bits. Okay, let's go for it. Let's go for it. Can I not move these ones? Oops. Alright, it doesn't want me to move these things, which is kind of annoying. Okay, so first things first, let's get our... we have 8-bit, nots and ors, negate and add, 8-bit switches. Three, 4, 5, 6 switches, which are going to be controlling whether we run the original input or the inverted input. Okay, then those wire together. And they go into an 8-bit breakout. Okay. Oops. And then delete that. Select all of this. Same deal. Okay. Now, let's break out our instruction byte. So 0 is OR, 1 is NAND. Okay, which means we want the non-inverted version of our inputs when 1 is high. And we want the inverted when it's low. Okay. Now, we're gonna want, where's my NANDs? 1, 2, 3, 4, 5, 6, 7, 8. And then those all come together. And then we're gonna have a couple more switches, like here and here. And that's gonna also need a NOT. Let's check the level log again for bit 2. So bit 2, when it's high, we invert. Okay. So this will be the inverted one, hooked up to bit 2. And this will be also hooked up to bit 2. And then that will be an 8-bit negator right there. And then our outputs run together like so. All right. Now I just have to get everything wired up. 1, 2, oops. 2, 3, 4, 4, 5, 6. What are the chances that I got this right the first time? 8. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay, let's see if I got this right. No. Oh. But only... Oh, well. Input 1, input 2, desired output. So the code is AND, which means that we should be using, the non-inverted path on the input, and then the inverted path on the output. Okay, let's just re... $64, 128, 128. Okay, so our code is AND, which means that we should be 17,178, 17,178. We NAND those together, and then we negate them. What is 17 and 178? That's a question. How do I do this in here? Catalog. Function. And. Nope. Well, that's 50, which is 32 plus 16 plus 2. So this should be... Well, I guess we can look, right? High, 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 high. Low, high, high, high. Okay. And then negating that. Why is that giving me a 17 instead of... Because this is a negative, not a negation. I want a not. And now it works perfectly. 8-bit AND, 8-bit NAND, 8-bit NOR. I don't get my 8-bit logic unit that I just spent all this time building out of NAND gates? Oh, come on. I worked so hard for that 8-bit logic unit. Okay, what do we get here? Whoop. Add addition and subtraction to your circuit. Oh boy. So yeah, this is good. Now I get an ALU. Okay. Okay. So yeah, bit 4 combined with our bit 1. Okay. So we're gonna put another 8-bit switch in here. Which is going to be not bit 4. What a mess. Okay. And then if we do have bit 4, we have an adder, we have a neg, we're going to have 2 switches. So we negate on bit 1. And just add. So that's output 2, which comes from here. Output 1 is always just output 1. And then we have one more 8-bit switch, which takes the output, sends it here if bit 4 is high. All right, unlocks manual component factory. Open the component factory by clicking on this button in the upper left bar. Allows you to create your own components. The logic you place determine the behavior of the custom component, and the layout determines the shape. The input and output components you place become pins on the component. Like with other components, a component leading back to its okay. Display values inside. Probes can be connected to other custom components so that deeply nested values can be displayed. Values probed in this way can also be connected to the program component. For the component factory, the file manager also manages the custom components. Okay, so now I can build like sub-assemblies, so I could save this ALU if I so desired. Welcome to the component factory. The circuits you create in here will be useful. Components can be added, renamed, or deleted. You can go to the level map and continue when you want. Okay. Okay, it does let me do this, though. Do I have access? Oh, I do have access to the component factory now. Open instructions in the top bar. Ah, cool. It shows you the register 0, reg 0. Cool. But I think I'm going to leave this one for switch schematic. This is my ALU, which is not super compact. I go back, custom. Oh yeah, look at that. I can put my ALU in. And it'll have to, I assume. Oh no, it can route under. Can it? No, it can't route. It has to sort of route around. Okay, so it is worth getting this like input layout cleaner. I'm not actually going to use that. This one's just tedious. I know what I need to do here. But I think I'm going to call it for tonight and jump back onto this, I don't know, tomorrow or sometime later this week, whenever my next stream is. Thanks to anyone who tuned in, and I will see you all next time.